Welcome everyone. We are Team Micro UAV. We started the project before the summer started. It's been 2 semesters before that, and it kind of began after seeing a presentation by Professor Shaw, who is a structures professor in the aerospace department, and the lecture was on micro air vehicles and flapping wings and the like, and it really just influenced us to really get in and sink our teeth into it and see if we can maybe make some changes or kind of build on what's already out there. So this started again as a direct study 2 semesters ago, and then we had the honor to do it over the summer as well through the SURE program. In terms of how we're going to do this, we were looking to build a smaller, lighter, and stronger vehicle that also has the control system, so it's more intelligent as well. The benefits to this project, and kind of again something that kind of pushed it along, was it's fairly cheap in terms of all the RC components, so it was a big advantage.
I came into the project trying to make the aircraft smaller. A lot of the quadcopters you see, they're fairly large, and I had the idea that we could make something quite a bit smaller that would still carry a good payload, cameras or sensors or whatnot. The circuit board I designed myself. We shipped it out to a fabrication facility that manufactured it to our specification. In terms of the quad rotor itself, we're trying to miniaturize everything, try and get the smallest motors we can, the smallest diameter rotors, the smallest everything. Right now we're looking at a quad that's be able to lift 160 grams of total capacity with payload. So we're looking at approximately an 80-gram payload on something that's about 8 inches in diameter.
The thrust stand that we built in order to make accurate measurements of the thrust and torque required to turn the rotor, and eventually the power required to run the rotor, was built from the ground up. And it utilized an architecture in which we used 2 separate instrumentation amplifiers for each load cell, signal traveling through 2 sets of instrumentation amplifiers, allowing for a reduction in noise produced. From the instrumentation amplifiers, we fed the signal to a AD converter, which converts the signal from analog to digital signal, and we're then able to send it via a microcontroller through a serial port to a computer, allowing us to log the data in real time, improving both the rate of measurement and the accuracy of measurements. After utilizing the 3D printing lab to produce our rotors, we realized this could be a good procedure and material to use for the frame of the quadricopter. It allows us to both produce complex geometries which are very small, and also allows us to keep them very lightweight. The material used in the 3D printing, Accura 60, is a polycarbonate plastic simulate, which simulates all of the material properties of the polycarbonate. However, the material does display more viscoelastic properties than desired, but for our purposes, the viscoelasticity really only gives us a problem in creep. So when we set the UAV down, basically the arms could start to sag. Since we had the ability to produce small, complex geometries, we had the idea that we could use a truss structure to reduce the weight of the frame in general, while still maintaining a high level of strength. We evaluated this by producing several small truss arm test sections, and were then able to load them both dynamically and statically to evaluate our FEA model. Through material testing and the analysis of the truss arms, we were able to confirm that our FEA is well within accuracy for our purposes. From this, we were able to design the finalized airframe for the quadricopter, which is a one-piece design utilizing the same truss structure for the test structures. However, the new structure is tapered and is optimized for the loading and for the creep, as we mentioned earlier.